It sounds like a line designed to wake you up this object passed closer than the moon. It suggests a near miss, a brush with danger, a rock slipping through a gap that was never meant to be tested. And the first problem is that your brain treats the moon like a fence line, as if anything inside that distance must be an emergency. But space does not work with fence lines. Space works with orbits, timing, uncertainty, and geometry. So tonight we're going to do something simple and surprisingly calming. We're going to turn that headline into a clear picture. What does closer than the moon actually mean? How do we know it happened? What can we measure about the object? What can we not know right away? And what this kind of close pass does and does not imply about the future. First, we need one steady reference point. The moon is far away by human standards and still close by astronomical standards. Its average distance is about 384,000 kilometers, and that number is used so often that it becomes a unit of its own. Astronomers will casually talk about lunar distance, meaning roughly the Earth-Moon distance. When you hear closer than the moon, it usually means the object passed within one lunar distance, inside that rough circle. That might sound like an object entering Earth's personal space, but it is more like a plane flying over your continent at high altitude. It is close only because our normal scales for space are so huge. Now let's name the feeling that headline creates. The feeling is that something came toward Earth, and we only found out at the last second. Sometimes that fear is justified in one narrow sense. Some small objects are discovered late, because they are faint, fast-moving, and hard to see against the sky. But another truth sits right beside it. Objects passing closer than the moon are not rare on cosmic timescales, and not even extremely rare on human timescales. Many are small, many are found in advance, some are found after they pass, and almost all of them are harmless in the same way that most lightning in the distance is harmless to you personally. It is real energy, real physics, but it is not automatically a disaster. So what do we know when an object passes closer than the moon? We start with the most basic thing: we know it existed and we know it moved. The way we know that is not by watching it like a plane in the daytime. We know it as a point of light recorded in images shifting against a background of stars. Survey telescopes take repeated exposures of the same patch of sky. Stars stay fixed in place. The object moves. Software flags the motion. Astronomers measure its position precisely down to fractions of an arc-second, and those measurements, called astrometry, become the raw material for determining an orbit. At the first moment of discovery, what we know is actually a small handful of facts. We have a short track of positions over a short time, maybe minutes to hours. From that, an orbit can be estimated, but it is uncertain. The orbit is not a single razor line. It is a cloud of possibilities that all fit the early data. And here is where the story often becomes dramatic in public, because uncertainty in orbital mechanics behaves in a very specific way. A tiny uncertainty in velocity early on turns into a larger uncertainty in position later. So the first orbit solutions can look like a corridor of possible paths, and Earth might be inside that corridor for some future time, or it might not. That corridor narrows as more observations arrive. Most scary-sounding early announcements are not predictions of impact. They are requests for more data. But your headline is about something that already happened. It passed closer than the moon. That shifts the question. If the close pass has already occurred, then we can often know the miss distance fairly well, because the object's track across the sky and the timing of its closest approach are now anchored by observations on either side of the encounter. Even if the object was discovered late, once you know it passed, you can often reconstruct where it went with good precision. In many cases, the uncertainty in closest approach distance becomes small quickly. So the next thing we know is the distance of closest approach, usually expressed in kilometers, or as a fraction of lunar distance. But there is a quiet trick hidden inside. That number closest does not always mean closest to the surface. It usually means closest to Earth's center, because that's how orbital calculations are often framed. And when you think about that, you realize the number can sound smaller or larger, depending on the reference. The moon is far away. Earth is big. A pass that is closer than the moon might still be hundreds of thousands of kilometers from the surface, which is still safely outside the region where Earth's atmosphere matters in any way. It is also usually far beyond the orbits of most satellites, though some passes can approach the altitude of geostationary satellites, which live around 36,000 kilometers up. A pass inside lunar distance is not automatically near satellites, and not automatically near the atmosphere. It is simply inside a large familiar benchmark. Now we come to what most people want to know next. What is the object? Is it an asteroid, a comet, space debris, a secret spacecraft, an interstellar visitor? The honest answer is that in the vast majority of cases it is an asteroid, a small near-Earth object on a solar orbit. Space debris can pass through similar regions, but it tends to have different motion patterns and is usually tracked by different networks. Comets can come close, but they are less common in these very close-fast headlines. Interstellar objects are extremely rare. The default explanation is a near-Earth asteroid. So what do we know about an asteroid from a point of light? We can estimate its brightness, and from brightness we can estimate a size range. But size is not measured directly from visible brightness, because brightness depends on reflectivity. A dark charcoal-like asteroid reflects little light and can look dim even if it is relatively large. A bright stony asteroid reflects more light and can look brighter at the same size. Without knowing reflectivity, the best you can do from visible light alone is a size estimate with uncertainty. Often early reports say something like 10 to 30 meters, or about the size of a bus or the size of a house. Those are translations of uncertain estimates. If the object is observed in infrared, the picture improves. Infrared sees heat, and heat emission depends more directly on size. Radar, if available, improves it even more, because radar can reveal distance, velocity, and sometimes shape and rotation. But radar requires the object to be close enough and the geometry to be right. Many small objects that pass quickly are not accessible to radar. So often what we truly know about size is a probability range. We also know something about the object's speed relative to Earth. This is not just a single number either. There is the heliocentric speed, the speed around the Sun, and there is the geocentric speed, its speed relative to Earth during the encounter. An object can pass close with a relative speed of a few kilometers per second, or tens of kilometers per second depending on orbital geometry. That speed matters because it shapes how long the object stays observable during the close approach and how quickly it moves across the sky. A fast object can cross the telescope's field quickly, leaving fewer chances to observe it. That is one reason late discoveries happen. Now here is a key point that makes closer than the Moon less frightening and more understandable. Close approaches are common because orbits cross in distance, not in time. Many near-Earth objects have orbits that intersect Earth's orbit. But intersection of orbital paths does not mean collision. A collision requires that Earth and the object arrive at the same place at the same time. Usually they do not. Earth is a moving target, but it is also a small target compared to the scale of space. Most of the time, timing does not align. A close approach is just a moment when timing aligned enough to bring the object near, but still not aligned enough for impact. So why do these close passes happen at all? Because the solar system is dynamic. Asteroids are nudged by gravity over long periods. Close passes by planets can shift orbits. Even subtle forces like the Yarkovsky effect, a tiny push from uneven heat radiation, can slowly alter an asteroid's orbit over years. In other words, the population of near-Earth objects is not fixed like museum pieces. It is a living swarm of trajectories, mostly stable, some slowly evolving. Now, when an object passes closer than the Moon, one of the most important questions is, did Earth's gravity change its orbit? The answer is almost always yes, at least a little. During a close pass, Earth acts like a gravitational lens bending the object's path. The closer the pass, the stronger the deflection. For most lunar distance encounters, the deflection is real but not dramatic. It changes the orbit slightly. But slightly in orbital mechanics can matter over long time scales. A small change now can lead to a larger positional shift years later, simply because the object travels millions of kilometers and small differences accumulate. This is where a certain kind of fear arises. If Earth can change the orbit, could the close path set up a future impact? The calm answer is it could in principle, but that is exactly why tracking exists. There is a concept in planetary defense called a gravitational keyhole. A keyhole is a tiny region in space during a close approach such that if the asteroid passes through it, Earth's gravity redirects it onto a future path that intersects Earth on a later return. Keyholes can be surprisingly small, sometimes kilometers wide or less compared to the vast distances involved. And the monitoring question becomes, did the object pass through a keyhole? In most cases, the answer is no. In nearly all cases, the refined orbit after the encounter rules out future impacts for decades or longer. But the existence of keyholes is one reason close approaches are treated with careful math, not casual reassurance. So what do we know after the pass? We know the orbit better. We often know whether there are any future close approaches that matter, and if the object is large enough to be of interest, it may be added to public risk tables for continued monitoring. Here another misunderstanding appears. People see risk table and imagine a list of incoming threats. But risk tables are often lists of objects with non-zero computed probabilities based on uncertainty ranges not objects expected to hit. And those non-zero probabilities often go to zero as more data arrives. The risk table is part of the system working, it is transparency about uncertainty. Now let's return to the specific headline again and pull out what it implies. This object passed closer than the Moon implies that we have measured an approach distance smaller than lunar distance. What we know implies we have at least the basic orbit, the timing, and a first characterization. But because you did not name a specific object, the most responsible and useful script is not to pretend we know its designation or exact size. Instead, we build an engaging story around what is typically known in these cases and how the facts are determined. That way the listener gains real understanding and the headline becomes less mystical. So imagine the moment of discovery. A survey telescope, perhaps scanning in the early morning hours, flags a moving point of light. It is faint, which suggests it might be small or far or dark. But then the motion is fast across the frames, which suggests it is not far. The combination faint but fast often means small and close. Follow-up observations are requested quickly because time is short. The object is moving and it will fade as it recedes, and it might be lost if not tracked. Within hours, orbit solutions are posted. Early solutions might show a close approach. The phrase within lunar distance appears, and here the world divides into two experiences. Most people never notice. A small subset of people see a headline and feel a jolt. In control rooms and observatories, the mood is different. The mood is focused. A close approach is not automatically alarming to them. It is interesting. It is an opportunity to refine an orbit to observe rotation, and shape sometimes to learn about the near-Earth population. It is work, not fear. As data accumulates, the orbit uncertainty collapses. The closest approach time becomes clear. The missed distance becomes a narrower number. The object passes. If it was small, it might never have been visible without a telescope. But the Earth notices in a different way gravitationally. The object's path bends. Its orbit around the Sun after the encounter is not exactly the same as before. After the pass, analysts look at the post-encounter orbit and ask a set of calm questions. Is the orbit now more Earth-crossing or less? Does the object have any predicted close approaches in the next few decades? How large might it be given brightness measurements across different angles? Does it show a light curve, a periodic brightening and dimming that implies rotation? Sometimes the light curve can tell you if the object is elongated, tumbling or rotating quickly. A fast rotation can suggest a cohesive structure. A slow complex rotation can suggest a rubble pile. These are not definitive, but they are clues. If the object was close enough and bright enough, it might be observed by many telescopes across the world in a short time. That can produce a richer data set. Spectroscopy might be possible, revealing the surface type stony carbon-rich metallic. Radar might be possible, revealing shape and size more directly. But in many closer than the Moon cases, the object is small and fast, and the observational window is short. So what we know remains basic orbit brightness, estimated size range, and a sense of whether it belongs to a known asteroid family. Now the next question listeners often want answered is why didn't it hit? And the simplest answer is also the most important, because Earth is small compared to the size of the orbital intersection region, and because timing matters. The object passed close in space, but its trajectory missed Earth. Close in space can still be tens of Earth diameters away. The Earth's diameter is about 12,700 kilometers. An object passing 50,000 kilometers away is roughly 4 Earth diameters from the center far above the atmosphere and still close compared to the Moon. An object passing 200,000 kilometers away is extremely far from Earth's surface in any practical sense, yet closer than the Moon. The phrase compresses a wide range of missed distances into a single dramatic comparison. And that leads to an important clarification. Closer than the Moon does not mean almost hit. It means closer than a well-known benchmark. Sometimes it truly is close in a technical way, close enough that geostationary satellite operators pay attention. Sometimes it is simply inside lunar distance, still far away. The Moon is a big circle. Another question is, could we stop one if it were actually coming? The answer depends mainly on time. If an object is discovered years in advance, deflection is theoretically possible with small nudges. If it is discovered days in advance and it is small, the best response might be warning and local preparedness. But remember the main truth, most small objects that pass close are not dangerous. A truly threatening object is one of sufficient size, and those are usually easier to detect earlier because they are brighter and can be observed farther away. The scary scenario is a medium-sized object not enormous, large enough to cause serious regional damage, but small enough to be missed until late. That is exactly why surveys are improving. Now, since this script is meant to be engaging, the best way to hold attention is to take the listener through the quiet logic of certainty. The more you understand how we know what we know, the less the headline feels like a mysterious near miss, and the more it feels like a tracked event in a monitored sky. So let's slow down and walk through the core information categories one by one in a way that feels like peeling back layers. First is time. We know when the closest approach happened, sometimes down to seconds. That sounds magical, but it is built from repeated measurements and gravitational modelling. The object's position at many times is fit to an orbit. From that orbit you compute when it is closest. More data points refine that. The time becomes a fixed marker. Second is distance. We know the closest approach distance within an uncertainty. That uncertainty can be small if the observation arc is long enough and the measurements are good. The distance might be reported as kilometres, or as lunar distances, or sometimes as a fraction of the distance to geostationary orbit. Each is a different way to anchor the same fact. Third is trajectory direction. We know where it came from in the sky and where it went. That tells us about the orbital inclination, and whether the approach was from near the sun's direction, which can make discovery harder, or from the night side, which can make it easier. Fourth is size estimate. We know brightness and can infer size range. We may not know exact size without radar or infrared, but we can bound it. Fifth is energy if impact. This is where fear tends to spike, but the calculation is simple. It depends strongly on size and speed. If a small object hit, it might create a bright fireball and an airburst. If a larger one hit, consequences would be more serious. But again, potentially hazardous and close pass are categories, not prophecies. Sixth is future risk. We can project the orbit forward and see future close approaches. This is the part the public cares about most and the part the monitoring system is designed to answer. If future impacts are ruled out, the story becomes simply a close flyby. If future close approaches exist, the object stays on watch. Now, a quiet and deeply interesting point, the orbit projection is not just a single line. It includes uncertainty and gravitational interactions. Over long time spans, close encounters with planets amplify uncertainty. That is why you will sometimes see risk tables list possible close approach dates decades away. Those are not predictions of impact. They are if-then statements. If the uncertainty includes a path that passes through a gravitational keyhole, then a later return could be close. The goal is to shrink uncertainty enough to remove those if-then paths. So what do we know really? We know enough to tell whether the headline is a moment of drama or simply a moment of measurement, and most of the time it is measurement. At this point it's worth addressing the most cinematic fear that we were almost hit and only barely escaped. That fear feels satisfying in a story way, but it is usually not accurate. A close pass inside lunar distance can be safe by a margin that is enormous compared to Earth's atmosphere. The atmosphere is only about 100 kilometers thick in the sense that matters for entry. An object can miss by tens of thousands of kilometers and never interact with the air at all. It is not like a near miss on a highway. It is a near miss in a volume of space where the lanes are unimaginably wide. Now let's make the story more vivid with a mental picture. Picture Earth moving along its orbit, a steady arc around the Sun. Picture the Moon orbiting Earth, a smaller circle around our planet. Now picture an asteroid on its own solar orbit cutting through near-Earth space. The asteroid's orbit is a long ellipse. Earth intersects that ellipse in distance at certain points, but the asteroid is not always at those points when Earth is. A close approach happens when the timing lines up enough, and even then, because Earth is a small target, it often passes with a large safe clearance. That is what most closer than the Moon flybys are, timing alignments that produce closeness, not collision. Sometimes these flybys teach us something practical about impact probability. The public often overestimates the likelihood of impact after a close pass, as if closeness increases fate. But in orbital mechanics, closeness can actually do the opposite. It can provide data that reduces uncertainty and clarifies that the orbit is safe. The flyby becomes a measurement opportunity. It tightens predictions. It reduces future risk estimates. It makes the object less mysterious. Now there is still one honest caution. Close flybys remind us that we live in a cosmic environment where rocks do move near Earth. The hazard is real in the long run. It is not a fantasy. But the correct emotional response is not dread. It is respect plus preparation. The preparation is already happening through surveys, orbit monitoring, and in rare cases deflection demonstrations. So as we approach the end of this script, we bring the headline back into focus and translate it into a steady conclusion. This object passed closer than the Moon means the object's closest approach distance was inside one lunar distance, a common astronomical benchmark, not a magical boundary. What we know usually includes the time of closest approach, the missed distance with some uncertainty, the object's path through the sky, an estimated size range based on brightness, an estimate of speed, and a refined orbit after the encounter that can be projected into the future for risk assessment. The most important thing we often know, and the thing headlines rarely emphasize, is that the object did not hit, and that with additional observations, future impacts are usually ruled out for a long time, often completely. And if you want one final thought that turns this from a headline into a calm understanding, it is this: the story is not that Earth narrowly escaped without knowing. The story is that Earth is in a well-tracked neighborhood, and the closer we watch, the more we discover, and the more we discover, the more often we will see objects pass close in the only way space allows, by ancient geometry, by timing, by gravitational choreography. Each flyby is a reminder that the solar system is active, and also a reminder that knowledge turns the unknown into the predictable. The object came closer than the Moon, and then it went on its way, returning to the long, silent work of orbiting the Sun. Earth continued too, turning steadily beneath its thin atmosphere. The Moon kept circling patient and distant, and the sky remained what it always is: vast, dynamic, and measurable, more understandable every year, not because it becomes less dangerous, but because we are learning how to read it with clearer eyes. Ba moi fucho video James Webb just found something that shouldn't be there just sui, ni trombo moi lamgie. In the first few 100 million years after the Big Bang, the universe is supposed to be wrapped in a kind of cosmic fog. Not a fog you could see with your eyes, but a fog made of neutral hydrogen-hydrogen atoms that have not yet been stripped into charged particles. And that detail matters because neutral hydrogen is very good at swallowing a particular kind of light, Lyman alpha, a bright ultraviolet glow produced when hydrogen atoms are excited and then relax again. In the early universe, that light should be smothered almost immediately. It should not travel far. It should not escape cleanly from distant galaxies. It should not arrive here across 13+ billion years of space and time with enough strength for us to detect it. And yet that is exactly what the James Webb Space Telescope has now seen: unexpectedly strong Lyman alpha emission from a galaxy so early that by the usual story the fog should still be thick. That is the something that shouldn't be there. Not a monster in the dark, not a new law of physics written in neon, just a clean beam of ancient light showing up earlier than the universe was supposed to allow, like finding a lighthouse shining through a storm that should have drowned it. To understand why this is such a big deal, we need to slow the story down and let the early universe become a place you can picture. After the Big Bang, the universe expands and cools. Early on, everything is hot enough that matter exists as plasma, electrons, and nuclei not bound together. In plasma, light does not travel freely for long. It scatters constantly. But as the universe expands, it cools. Eventually, around a few 100,000 years after the Big Bang, electrons settle onto nuclei forming neutral atoms. This is called recombination, and it is when the universe becomes transparent in a broad sense, allowing light to travel long distances. That ancient light is still around today as the cosmic microwave background stretched by expansion into microwaves. But transparent does not mean fully clear for every wavelength. Neutral hydrogen, abundant everywhere, at first creates an era sometimes described as the cosmic dark ages, not because the universe is literally dark, but because the first major sources of starlight have not yet reshaped it. The first stars ignite, the first galaxies begin to form, and over time their radiation starts to reionize the universe, stripping electrons off hydrogen, again turning neutral hydrogen into ionized hydrogen. This process, called reionization, is thought to have unfolded gradually and to have been largely complete around 1 billion years after the Big Bang, though the details are still an active area of research. Here is the crucial point: if the space between galaxies is still filled with lots of neutral hydrogen, Lyman alpha photons should be absorbed and scattered away. So when astronomers look at extremely early galaxies from just a few 100 million years after the Big Bang, they expect Lyman alpha to be weak or absent because the fog should swallow it. Webb, however, has the sensitivity and infrared vision to see galaxies at redshifts that older observatories could only dream about. Redshift is the stretching of light as the universe expands. Higher redshift means farther away and earlier in time. Using deep imaging from Webb's near-infrared camera as part of the JADE survey, astronomers identified an extremely distant galaxy called JADE's GSZ 13.1. They then used Webb's near-infrared spectrograph to confirm its redshift at about 13, meaning we are seeing it as it was roughly 330 million years after the Big Bang, a staggeringly early moment. And then the spectrum revealed an impossible feature-bright Lyman alpha emission much stronger than expected at that epoch. So what could this mean? There are a few broad categories of answers, and the most interesting thing is that every category teaches us something important. One possibility is that the early universe was not uniformly foggy. Even in the standard picture, reionization is not expected to happen everywhere at once like a light switch. It is expected to be patchy like holes forming in clouds. Regions near intense early sources, clusters of young galaxies, or particularly bright galaxies, or energetic black holes could create ionized bubbles in the surrounding hydrogen. In those bubbles, Lyman alpha can travel farther before being absorbed. So Webb seeing Lyman alpha could mean we are catching a galaxy that sits inside an unusually large bubble of ionized gas carved out earlier than average. The universe at 330 million years might not be clear, but it might have rare clearings. But even that is not supposed to be easy. A bubble large enough early enough to let that line escape so cleanly would imply intense radiation fields very early, either from a galaxy forming stars at a furious pace, or from something even more efficient at energizing and ionizing gas. That leads to another possibility: something inside the galaxy itself is doing extra work, changing its local environment in a way that makes Lyman alpha easier to see. Imagine the galaxy not as a quiet island of stars, but as a compact furnace of radiation, stellar winds, and violent feedback. If the galaxy is forming massive stars quickly, those stars pour out ultraviolet light that ionizes surrounding gas. Supernovae and stellar winds can also punch channels through gas and dust, creating paths of lower density where photons can escape. If the galaxy has unusually strong outflows, it can shift the Lyman alpha line in frequency in a way that makes it less likely to be absorbed by neutral hydrogen along the way. The details here are subtle, but the idea is simple: the galaxy might be creating its own escape routes. And then there is the most dramatic possibility, the one that has become increasingly relevant in the Webb era: an active, supermassive black hole, a young black hole feeding on gas, producing intense radiation from the hot material swirling around it. That radiation can be extremely efficient at ionizing gas. If a growing black hole is present, it could help create and maintain a local ionized region that lets Lyman alpha escape. NASA's own discussion of the discovery emphasizes the surprise and the challenge of explaining how such light could pierce the neutral hydrogen fog at that time, which is exactly the kind of puzzle a hidden energetic source could address. If this sounds like we are edging toward a bigger theme, that is because we are. Webb keeps finding signs that the early universe may have produced bright, compact, energetic objects sooner than our simplest expectations. Sometimes this shouldn't be there. Headline is about light escaping too early. Sometimes it is about galaxies seeming too massive too early. Sometimes it is about black holes appearing too grown up too soon. The details vary, but the sensation is similar. The early universe seems to be less patient than we thought. To keep this grounded and honest, it helps to remember how science handles a phrase like "shouldn't be there." It does not mean impossible. It means unexpected under the most common model assumptions. It means this observation sits in a region of the map where our confidence was strong, and now we need to update the map. When Webb first began returning deep images, some teams reported candidate galaxies that looked surprisingly massive at extremely early times, which raised questions about how quickly structure can assemble. Over time, the community has been sorting which candidates hold up under spectroscopic confirmation and which were misestimated due to dust emission lines or photometric uncertainties. That pattern is normal in frontier science: early excitement, careful follow-up, and then a sharper story. The universe rarely breaks. Our first interpretations do. The Lyman alpha case is especially powerful because it touches a major cosmic milestone, the onset of reionization. The timing and patchiness of reionization are not just trivia. They connect to how the first stars formed, how the first galaxies grew, and how early black holes behaved. In the standard narrative, reionization is a drawn-out process, with the universe gradually transitioning from neutral to ionized over hundreds of millions of years. Seeing strong Lyman alpha at redshift around 13 suggests either that reionization began earlier in some regions than we expected, or that certain sources were far more efficient at clearing local paths than our simpler models assume, or both. Now let's make this feel less abstract by imagining what Webb is actually doing when it makes such a discovery. Webb does not see a label that says galaxy at 330 million years. It sees infrared photons. It measures their distribution in wavelength. In a spectrum, astronomers look for signatures, sharp rises, emission lines, absorption breaks that act like fingerprints. When the light has been stretched by the expansion of the universe, those fingerprints shift toward longer wavelengths. By measuring how far the shift is, astronomers estimate redshift. Webb's instruments are designed for this deep infrared imaging to find candidates, then spectroscopy to confirm. For JD's GSZ 13.1, the imaging suggested an extreme redshift and the spectroscopy confirmed it, then revealed the unusually bright Lyman alpha feature. That feature is not a vague glow. It is a specific wavelength signature from hydrogen, and it is bright enough to demand an explanation. This is where the story becomes quietly thrilling, because the explanation could reshape how we picture the earliest phase of galaxy formation. If the universe can produce pockets of clear space earlier than we thought, then early galaxies might have influenced their surroundings faster. If early black holes were present in more systems than expected, then black holes might have played a larger role in ionization than we assumed. If stellar feedback creates escape channels more efficiently at low metallicity and high star formation density, then the earliest galaxies might have been better at punching holes in the fog. And this is where another Webb mystery links in perfectly: the so-called little red dots. These are compact, bright reddish objects seen by Webb at high redshift that were puzzling because under one interpretation, they look like massive galaxies too early to exist in that mature form. Recent work reported in Nature and summarized by major science outlets argues that at least many of these little red dots are better explained as young, growing supermassive black holes wrapped in dense gas cocoons, objects that can shine brilliantly in the infrared while hiding typical X-ray and radio signatures. Under this interpretation, the inferred masses drop significantly compared to earlier estimates, helping bring them back into agreement with standard evolutionary expectations. Notice what that does for our main mystery. It suggests that the early universe may contain more black hole-powered light sources than we previously recognized, but many of them may be hidden, disguised, or misclassified when we rely on older assumptions. If that is true, then a galaxy like JD's GSZ 13.1 showing unexpectedly strong hydrogen emission could be connected to similar physics-intense local radiation fields, possibly from a central accreting black hole that help carve ionized regions and let certain photons escape. That does not prove anything by itself, but it frames a plausible family resemblance among Webb's shouldn't be there discoveries. The early universe may have had energetic sources that are easy to underestimate when you assume they must look like the galaxies we're used to nearby. At the same time, it is important not to turn this into a single dramatic conclusion too early. The honest scientific posture is Webb has found strong evidence that at least one extremely early galaxy shows Lyman alpha emission stronger than expected at its epoch, and this challenges researchers to explain how the light escaped the neutral hydrogen fog so early. Multiple explanations are under investigation, and further observations of this galaxy, and of other galaxies, at similar redshifts will show whether this is a rare oddity or a sign of a broader pattern. That is how the frontier moves. One object becomes a question, the question becomes a survey, the survey becomes a new model. Now let's step back one more level, because the phrase "shouldn't be there" also speaks to something human about cosmology. Cosmology tries to tell one consistent story from the first fractions of a second to the present day. That story is built on a set of measurements that mostly agree extremely well: the cosmic microwave background, the expansion of the universe, the distribution of large-scale structure, the abundances of light elements. Within that story, ionization is a chapter whose broad outline has been known for some time, but whose details, exact timing, patchiness, dominant sources are still being refined. Webb is now reading that chapter in sharper detail than ever before. It is not surprising that it finds sentences we did not anticipate. And there is a calm perspective here that makes the whole thing feel less like a crisis and more like a deepening. The early universe is not obligated to match our simplest simulations on the first try. Simulations are built from known physics, but they must choose certain starting conditions, certain approximations, certain recipes for star formation, and feedback that are tuned to the later universe where we have abundant data. The earliest galaxies live in a regime where the physics is the same, but the conditions are extreme: lower metallicity, denser gas, more violent radiation fields, and short timescales. It is exactly the regime where small differences in assumptions can produce large differences in outcomes. Webb is telling us which assumptions were too conservative. Now, if you want to feel the timeline of impact in your mind, how one impossible line in a spectrum changes what researchers do here is how it tends to unfold. First comes confirmation. Extreme redshifts are not accepted lightly because the stakes are high and the delta is challenging. Webb's spectroscopy is essential here. Then comes modelling. Teams ask what ionized bubble size would allow this Lyman alpha signal to emerge, what star formation rate would be required, what escape fraction of ionizing photons would be needed. Could outflows shift the line enough to reduce absorption? Could there be a hidden active nucleus? Then comes comparison. Do other galaxies at similar redshift show anything similar? Is this an outlier or the first example of a class? Webb surveys like JD's are designed for exactly this, building statistical samples rather than one-off marvels. Then comes cross-checking with other observatories. If ALMA can observe the dust and gas content, it can constrain star formation and the interstellar medium. If future X-ray observatories look for hidden accretion, they can test black hole involvement. If ground-based telescopes with powerful spectrographs can confirm related properties, they can add confidence. Finally comes theory revision. If the data demands earlier pockets of reionization, models must accommodate that without breaking everything else. That is the art. You can't just turn reionization on earlier everywhere because other data constrains it. But you can adjust the patchiness, the brightness distribution of early sources, and the efficiency with which early galaxies let ionizing photons escape. That last phrase, escape fraction, is quietly central. A galaxy can produce many ionizing photons, but if those photons are trapped by the galaxy's own gas and dust, they do not reionize the intergalactic medium. Early galaxies may have had conditions that made escape easier, less dust, more violent feedback, and porous gas structures. If escape fractions were higher early on than in later galaxies, reionization could begin earlier locally, without requiring absurd star formation everywhere. Webb's Lyman alpha detection is a hint that escape in at least one environment may have been surprisingly effective. Now let's connect this back to the emotional core of the title. James Webb just found something that shouldn't be there. The reason this hits so well is that it suggests the universe is misbehaving. But the truth is gentler and more beautiful the universe is behaving, and we are catching it in a phase we have never observed this clearly before. When you build a timeline from the Big Bang to now, the early universe tends to become a simplified landscape. In the mind, first darkness, then first stars, then first galaxies, then reionization, then mature galaxies. Webb is showing that the early landscape had microclimates, regions where things happened earlier, faster and more intensely than the average. A galaxy can clear its neighborhood sooner. A black hole can grow inside gas that hides its usual signals. A bright hydrogen line can escape where it should have been absorbed. These are not violations, they are texture. And once you accept texture, a lot of other Webb surprises become easier to interpret. The early universe can look too bright because some objects are powered by accretion. It can look too structured because some galaxies settle into disks earlier than expected. It can look too mature because dust and emission lines can trick photometric estimates. And sometimes, yes, it can genuinely be ahead of schedule in ways that force models to evolve. If you want a second shouldn't be there thread to weave into this, you can think about the broader discussions around unexpected early light sources. Scientific American described Webb observations that raise questions about light sources appearing before the first galaxies should have formed, and explored ideas, including primordial black holes as speculative contributors, while emphasizing the uncertainty and the need for more evidence. That kind of discussion sits at the edge of what is known, and it is important to keep it there interesting but not overstated. The strongest anchor remains direct, well-characterized observations like the JD's GSZ 13-1 Lyman alpha detection, which is explicitly framed by NASA as a surprise that challenges researchers to explain early clearing of the hydrogen fog. So where does this leave us in a calm sense at the end of the story? It leaves us with a universe that is still broadly consistent with its major pillars, but richer in its early details than our simpler pictures captured. It leaves us with a specific testable puzzle. How could bright Lyman alpha emission escape from a galaxy at redshift around 13 when neutral hydrogen should have absorbed it? It leaves us with plausible answers that can be tested: patchy, early ionized bubbles, unusually efficient photon escape, strong outflows, intense star formation, and possibly hidden black hole activity. And it leaves us with a sense that Webb is not breaking cosmology, but tightening it, forcing it to become more accurate. And maybe the most calming thought is this: the early universe is not something we can ever visit. We can only read it in light. Webb has simply given us a sharper alphabet and a deeper page. Sometimes when you can read better, you discover that the story was more complicated than the summary you learned first. The summary was not wrong, it was incomplete. The fog was real, but perhaps in rare places it had holes earlier than we expected. And through those holes, for a brief moment in cosmic time, ancient hydrogen lit up, and the light escaped, crossing the entire expanding universe to reach a telescope built by a late civilization on a small planet. That light is not supposed to be there according to our simplest map. But it is there in the data, and now the map will change slowly, carefully and inevitably, until shouldn't becomes we understand why.